Alright guys, welcome to the next chapter of our networks unit, which is now chapter 9i on weighted graphs. The previous lesson we looked at Hamiltonian paths and cycles, so go ahead and watch that. That will help you understand more concepts about what we've been doing in networks. Now weighted graphs is the next chapter, and it's slightly different to the other sort of networks that we've been doing. So let's get into it. So a weighted graph is a graph where each edge, so each line, is given a numerical value. Okay, so each edge has a numerical value, and this value can represent time, cost, and distance, those sort of things. Okay, so you'll find that a lot of weighted graphs, okay, will have contexts to them added. But for now, we'll just do some simple basic ones. So the sum of a weighted graph, or the weight of a graph, sorry, so the weight of a graph. So when we ask for the weight, it's basically the sum of all the edges in its vertices. All the edges. The sum of all the weights of the edges, to be more precise and exact. So when we ask for the weight, that means we're asking for what is the total sum of the weights of all of these edges. So these examples, we're just going to add together the weights of each of these edges. So you can just go and do this really simply as 10. So that's that 10 plus the third 10 here plus 15, sorry, plus 11. That would be equal 30, 40, 50, 56. So the total weight here is 56. Okay. Simple. This one here, a bit more tricky. There's more numbers. Okay, but 12, 11, 10, 14. What I like to do is maybe cross out each one as I go. Or actually, so if you do this on your sack, maybe consider using pencil so you can rub it out, but I might circle them just so I can still see the numbers. So I've got 12, 15, 16, 13, 10, and 16. Okay. So adding them all up, you can use your calculator. Use this one. So I'll go 12 plus 11. Oops. There's no quick way to press plus here, which is annoying, but that's okay. Plus, where are we at? 10 plus 14 plus 12, 15, 16, 13. If Torio was a calculator, he'd smash this out real quick, but he's not. So the total weight of this graph is 128. Make sure that you included every single number. Chances are some kids, I know in the past, when they do these sacks, they'll miss some numbers. Okay, so just double check. So you got 12, 11, 10, 14, 12, 15, 16. Okay, there you go. I made a mistake here. I wrote, instead of writing 13 right here, I wrote 12, 10, 16. So again, it pays to double check. So it should be 129. Alright, so that's basically how you find the weight of a graph. Just add the value of all the weights of the edges. Okay, so what's that got to do with the network and the graph in total? Well, basically what you want to do is whenever you get a question that's got a weight in it, the idea is you want to find the shortest path between two vertices. Okay, and what that's saying is basically finding the path that's got the least weight between both vertices. Okay, and there's two methods for finding them: by inspection or intelligent trial and error. So just trial and error basically, or Dijkstra's algorithm. I would say both of them are actually quite similar. So when I go through this with you, when I teach you Dijkstra's, I will probably just do it the basic way because I find that Dijkstra's can get a bit confusing, but for now, well, let's see how far we get with it. But just some things to think about. Okay, so the shortest path. Okay, so if you were to try and find a short path from one vertex to another, it's not always going to be the path with the least number of edges. okay? Because sometimes those edges might have really big weights, like for example, that one and that one there. So you got to watch out for that. And the path formed is not always, it's not always about choosing the least weight depending on which edge you're at, okay? Because there could be a big weight later on. So for example, if I go 3, okay, that's fine. But then if you look at the adjacent edges there, you've got 12 and 9, which is quite high. Whereas if I went to 6, 8 is a pretty good option. Okay, it's better than going 3 to 12. Okay, it's 6 plus 8 is 14. 3 plus 12 is 15. So it's more. Okay, to get to E, the shortest path would have to be A to B to E. Okay, so those are some things to keep in mind when we do these. So let's do this. Actually, there's an example here. Let's do this example. So I want to go from, let's say from A to G. Okay, I want to find the shortest path from A to G. So to get to A to G, I'm looking at these two vertices. Okay, so what's the shortest path from A to G? I'm going to use trial and error. So I could go from 3 to 12, or A to C to D. That will give me A to C to D already. That's a weight of 12, plus the 13 to G would be 25. Okay, so A to C to D to G gives me a weight of 25. Okay, but is that necessarily the shortest? Well, let's see if there's any other better ones that we can go through. I can go A to C to D. D to E is quite small, so that's only 3. And then E to 9, E to G is only 9, so that's an extra 12. So that path there that I've taken, A to C to D to E to G, gives me a weight of, what is that, 24. So that's actually better than ACDG. Even though this has less edges that I've gone through, this has a smaller weight. Can we find any other smaller ones? Let's see. A to B is 6, to E is 14, plus the 9 there. Oh, okay, I think this one might be shorter. So A to B to E to F to G. Okay, to A to B to E to F and then to G. I think this one actually is a lot smaller. So A to, that's 6, 14, 19 plus 4 is 23. So that is a weight of 23. So that path, A, B, E, F, G, okay, only has a weight of 23, which is the smallest one so far. And I think that's probably the shortest one. You could go E to G as well, A, B, E, G, because that gives you the same weight of 9. It will give you the same weight. So both of those answers would be correct if I went A to B to E and then straight to G, because that would give you a weight of 23 as well. So that's actually quite good. But either of those answers would be correct because they would be considered the shortest path. Okay, but again, understand that sometimes the edge that's the smallest might not necessarily be the one with the shortest path. Okay, you'll have to find, the edge, that's the shortest from the start, might not necessarily be the best path. You might have to go through another path. So instead of going to A to C here, I went A to B. All right, so now we're going to look into using Dijkstra's algorithm. Now, just a quick caveat here. If you don't fully get this, it does get a bit confusing. So it will take a bit of time or a few tries to get used to understanding how this algorithm works. But what I'm going to show you is something that is used a lot in year 12, I believe. But it's also something that you don't have to use now in year 11. You can actually just keep doing trial and error if you want to find the shortest path. However, trial and error may take a bit of time. Doing it this way using Dijkstra's algorithm also takes a little bit of time, but will more or less get you the shortest path. Okay, so the idea behind this is basically similar to your trial and error, but what you're doing is you're starting at one vertex called the, or whatever it says here according to this, we have to find the shortest path from X to Y, right? So starting from one vertex, you're going to try and find the shortest path to the other vertex. And what you do is you keep following the shortest path from there. Now, easily said and done. However, the shortest path, based on what we've been given here, so things to be aware of, is it's not necessarily the one that has the smallest weight or the least adjacent weight on that edge. Okay, so what I'm saying is the shortest path isn't necessarily always the one where you take the smallest weight. Okay, because sometimes you might find that going this way takes longer than going maybe this way. Okay, and this is what Dijkstra's algorithm will do. It'll actually show you which one is the shortest path. Okay, so that's basically what this sort of entails, and these instructions tell you to do. But I'll show you an example of how to do it here as well. So this may take a bit of getting used to, so just prepare yourselves for this. So what you want to do is when you get a question like this, and you want to try and find the shortest path from one vertex to another using Dijkstra's algorithm, I like to draw a table. Okay, and the table just helps you to organize what's happening. So draw a table with 3 columns. Okay, this is what I like to do. Here are your vertices. So you're going to list out all the vertices in this graph. So in this case, you've got X and then A all the way to I. So just write all that: A, B, C, D, E, F, G, H, I. Oops. And the last one is Y. So don't forget to put the final vertex. So that's what you put in the first column. In the second column, now this is where it does get a little bit tricky, is you're going to write distance. Okay, distance from, okay, and what I'm going to write here is distance from the first vertex, the starting vertex, which is X. Because what this table is going to show you is it'll give you the distance, okay, from vertex X to every other vertex. Okay, so from vertex X to every single other vertex here. All right, so from there, that's what the middle column is going to be. The third column I'm going to write here is the previous vertex. Now this sounds a bit unfamiliar, but what this third column is actually, it's going to tell you the previous vertex, the last vertex from that current vertex you're looking at. So say for example you went through a certain path and you're at G. So for example at G, the previous vertex, and the one that will give you the shortest path is either E, okay, because the previous vertex from G is either E or it could be F. It depends on which one the shortest path, or what we found as the shortest path to be from X to G. Okay, and then say for example from F. All right, so if you're at F, the only previous vertex you have there is D. Okay, if you're at D, the only previous vertex you have is either A or either C. So it's either A or it could be C, but it depends on which one is the shorter one. So the shorter one will be listed out here to be the previous vertex. So let's fill out this table. All right, so for this, starting at X, okay, and then moving to Y, or trying to get to Y, let's go from there. So at X, the distance from X to X is basically going to be 0, okay, because that's our starting point. X to X is going to be 0. Okay, we've started there, and the distance to get to X from where you started is 0. Now, there are 2 options from X. I can see that you can go either to A or to C. So these are the 2 adjacent vertices that we haven't visited yet. These are considered the unvisited vertices. So from X to A, there is a distance of 2. Okay, so from X to A, there's a distance of 2. And you can write that up here if you like, the number 2. Although I see that there are a lot of numbers here, but it can get a bit confusing. So just keep in mind that from X to A, the distance is 2 there. From X to C, the shortest distance is 3. All right, so from X to C, the shortest distance was 3. And the previous vertex for both A and C was the vertex X. So in our previous vertex, we came from X. Okay, cool. So now from there, what you are most likely would want to do is select the path that's given you the shortest one so far. So far, X to A has been the shortest. So next, we start at A. And then we look at the vertices that have not yet been visited. So that'll be vertex D, vertex B. Now from A to B, there's a distance of 5. But remember, from A, there's already been a distance of 2. So from there, that being 2, we have to add it to the distance of 5. So that means from A to B, there's a distance of 5. But from X to B, remember, distance from X to B, that's where I got the 2 from. You're going to add it to the 5. So that'll be 7. Okay, 7. And the previous vertex that we came from to get to B was vertex A. From A to D, I can see there's a distance of 3. So from X to A to D, there should be a total distance of 5. X, A, D, 5. Okay, and I can see from there, that will be, we came from A. Right, so that means so far we've visited X, A, we've visited B, and we've visited C and D. Now, according to this, the shortest number that we've got, so we've gone through here for now. Okay, we've gone through here, X to A. Next, the shortest path is actually going to be X to D. Okay, because A to B, A to D. A to B so far is 5, A to D is 3. So now we're here. Make this more clear. So this is the sort of path we've taken so far. And we have visited B and we've visited C. So what's next? Next is from D, you can either go to E or to F. So from D to E, so we're at D at the moment. So far, to get to D from X, we were at 5. So from D to E, that'll give us 8. Okay, so 5 plus 3, because the distance there is 8. Or we could go D to F, which is 5. So 5 plus 5 will give you 10. And both of them, the previous would have been D. So we came from D there. Alright, so according to this, I would say that the shorter distance would be to go to E. Go with the shorter one the whole time. Alright, now from E, I only really have one option, which is to go to G. So from E to G, remember from E, we're at 8. Okay, so you've got 2, 3, 2 plus 3 is 5, plus 3 is 8. E to G would be 8 plus 6, which is 14. Okay, and the previous one to get to G was E. So we are now here. I've taken this path. Okay, now from G, you've either got H or you've got I. So G to H, so we're at G at the moment, we're at 14. G to H, so at 14, I got that from these numbers, yeah? I've added them so far. G to H, 14, G to H, sorry, 8, X to G so far is 14. To get to H, there's a 1 there, so that means 15. We came from G. Okay, and we can also go from G to H, I, which has a weight of 3. Okay, so if we go through I, that weight will give us, so if we're at G, remember we're at G, these numbers, given me 14 so far. And if I want to go to I, that would give me 14 plus 3, which is 17. So if I go that way, it'll give you a weight of 17. So far we're at G, so we're at either I or H, and we've got 17. Now, according to this, the shorter one would be to go to H, because it's 15. So we'll go to H. Keep in mind that the shortest adjacent vertex or edge, may not always be the shortest path. Okay, so just keep that in mind. Now, from H to Y, I can see that the shortest distance from H to Y, there's only one. We're at H at the moment, it's at 15. So if we add another 4, that'll be 19 from H. Okay, so that technically should be the shortest path that we found. Now, interestingly, you could actually also go this way, because if we're at I and it's 17, if you add 2, okay, that will also give you 19. So that's also short. But that essentially right there is our shortest path. Now, technically, what the information I've got here will give you enough to give you the answer, and you need to obviously write down the path of X, A, D, E, G, H, and then Y, and then give me the total weight for that. And the total weight for it was 19, right? So the total weight is 19. However, you can actually find the path that you should take based on these, which is what I mentioned earlier. And to do that, basically, if you're at Y, okay, if you're trying to get to Y, and you're at X, sorry, and you want to get to Y, you can backtrack. So firstly, if you're at Y, the previous vertex was H. Okay, so that means you go to H. And if you're at H, the previous vertex was G. Okay, and if you're at G, right here, the previous vertex was E. So we go to E, which is here. If you're at E, the previous vertex was D. So we go to D. So we're here. And then if you're at D, the previous vertex was A. So A would be this column here. And if you're at A, right here, my bad. And if you're at A, the previous vertex was X. So X being here. So that means the path that we took would be, well, X is right there, XA, XAD, GHY. Okay. Yeah, I think that's all. XAD. Oh, I skipped one. Sorry, here I noticed. If you're G, E. Oh, sorry. Yeah, G. I forgot to put this one in. My bad. Yeah, I think I rubbed that one out. Anyway, so X, A, D, E, G, H. And then obviously the last one would be Y. Now that does seem a bit confusing, but I find that if you understand how to do sort of this and just list out your numbers here, most of the time you should be okay. And also you can just use the trial and error way, which tends to be the method that really works for the most part, but sometimes you might not get the correct answer, or it might take you a bit longer to get the correct answer. All right, let's try one more example just to help you guys understand how this Dijkstra method works. So I've drawn my 3 columns here. First column, you've got your vertices. Second column, remember it's the distance from the first vertex, or the starting vertex. In this case, we're trying to get from X to Y, yeah, according to the question here. Trying to get from X to Y. So distance from X, from the X vertex, and here is the previous vertex. And this sort of will tell us, or will show us the quickest path to go from one vertex to the other. All right, so you've got your vertices starting from X. I can see that it goes from A to G, so I'm just going to go A, B, C, D, E, F, G, and obviously don't forget the final vertex Y, which is our destination. All right, so let's write down the distance from X to get to all of these. All right, so we're starting from X. All right, starting from X right here, X to X, the distance is going to be 0, and the previous, we'll just leave it as, or I guess X in this case. Or you can just leave that because it's going to be obviously the starting. So from X, we can either get to G with a weight of 9 or E with a weight of 10. So G, get there with a weight of 9 starting from X, or we can get to E right here with a weight of 10. So 10 from X. And then from there, what I like to do actually from here is think about all the paths that the vertices that you can visit from either of these. So from G, you can either visit A or F. Okay, so from G, okay, we're at G, there's a weight of 9. We can get to A with a weight of 15. So 9 plus 15 is 24 from G, the previous one. We can also get to F. So G, 9 plus 4 is 13. To F, 9 plus 4 is going to be 23. So these two are visited now. So to F, 23, and it was from G. Also, we can check from here that from E, you can also get to F and to D. So from E to F, from E, there is a weight of 10 plus 12 is 22. So E to F, F here has a weight of 23. There's a better one. Okay, from X. So sorry guys, from X to E to F, which gives you a weight of 22. So that's actually better than from G. So here we go from E. Okay, the previous one being E to F. Our previous one being F to G to F. Now it's going to be E to F because that's better, isn't it? From E, you can also get to D. So from E, you've got a weight of 10. So far we were at 10 here, and we can go to D with 24, which is 14. So add that up, equals 24. So that would be the previous vertex, which is E. So now so far we've visited all these vertices. Now we've got a few more vertices to visit. So we can go from A, we can visit B and C. A, so far you've got a weight of 24. Okay, and to get to B, it's 10. So 24 plus 10 is 34 from A. Or you can also go to C. Okay, 24 plus 12 would be 36 from A. Okay, so we visited B and C. But similarly from D, you can also visit C and Y. Okay, so from D, you're at 24 to get to C plus 15. So 24 plus 15 would be 39. Well, C's already got 36, so that's already better. So that's fine. The only other one we haven't visited is this one here, Y. Well, we're at 24 with D. All right, 24. So to get to Y, it's going to be 35. So 24 plus 35 is 59. That'll be from D. That is quite high. So we've visited that. But we haven't checked from B yet, have we? So from B, you've got a weight of 34. Okay, see that? Weight of 34. And to get to Y from B, you've got 14. So 14 plus 34 will give you 48, which is better than what we have here so far. So 48 from B. So there you go. All of our vertices have been visited. And these are the distances from the shortest distance from X. So if we're looking at Y, the shortest distance would be 48. Okay, but what's the path that we're taking? Well, let's look at what we've got here. So from Y, the previous vertex will be B. So B. So we're at Y, and then we go to B. And then so if we're at B, B's here. The previous vertex was A. So right here, A. So from A, up here, the previous vertex was G. And from G, the previous vertex was X. Just there. So the path that we've taken is this. Essentially X, G, A, B, and then Y. And the weight of it was 48. Or actually you can say the distance, depending on the context really. It could be distance, weight, time, but the distance was 48. Now I hope that that's made sense. If it hasn't, please ask me questions. I'm more than happy to help you through this. But in any case, Dijkstra's algorithm can get tricky. Okay, but if you do watch it a few times, you'll sort of get how to do it. Otherwise, trial and error also works, just might not give you the answer the quickest way. Okay, so now I'll do the questions for chapter 9i. Thank you.